We want something to view the memory in the Gameboy at some point in time. We'd want it to support all of the memory mapped I/O, not just the RAM. This is a little like our own hex dump, but we'll want to have more of an interactive interface. So before we get started, let's look at what other people did. We have hex dump, OD, XXD. Basically, these all look the same. They show bytes in a table. There's a Rust version, Hexel, by SharkDP that colorizes the output. This is pretty nice. Here we can also see the ASCII associated with the underlying byte values. We can also look at memory viewers in existing emulators. Messen shows the table with row and column labels clearly visible, but in a way that doesn't distract you from the content too much. And in this case, it looks like Japanese characters shown are corresponding to the specific bytes in some way, and they have this clear cursor that highlights which byte you're focused on. TEMU here, look on the right, makes the memory map clear in its visualization. And here we see VRAM is the familiar table. Emulatronia shows that memory is actually changeable. This seems like a nice feature to have, but maybe we'll add it later, whenever we need it. For now, let's just make a simple table because I really want to just ship this video already. But we'll include a cursor and the ASCII bits associated with the bytes that we're dumping. We should be able to focus on any particular part of the memory map and show some amount of rows and columns of bytes around that focal point. Since this component is a little bit more meaty, let's break it into two functions. One will do the dirty signal munging and handle projecting read-write handles out of our app state into a view model, but it will not have any component-specific view logic. The other function will just be a plain old viewModel arrow RC virtual node function that will invoke every time our signal commands us to do so, but itself doesn't know about signals. So our state for at least the view part of the component should be something like the following. We have local state t, which has a t for the focus and a t for the cursor, coupled with some invariants. The focus has to be at least 0x40, assuming we have 8 rows showing, and must be aligned to a 16-byte boundary. The cursor should be some memory location that is visible in our data vector, and this will keep our logic simpler in the component. The view model, as we say, has the actual byte data and is aligned with the data in the first row, not the data we're focused on. We focus in the middle of the data vector. And two local states. One, a value containing a U16 focus and a cursor, and two, a reference to the mutable wrapped in an RC ref cell such that Rust stops yelling at me. This mutable version lets us change the local state. In the end, we're returning a table with top labels and all data embedded inside of it. Top labels just formats all offsets as hex characters and wraps them in th HTML nodes. We chunk the model data into 16-byte pieces, assuming calls is set to 16. Then we draw a row for each chunk of data. We're about to nest some move closures, so we need to clone a lot. Draw row is a closure that runs once per each row. We map over the calls now in another nested closure. For each call, we compute the color, either transparent or pink if the cursor is on this position. And we set a click handler, which is another closure. Inside the click handler, we write the new cursor location into the mutable. Additionally, we compute the ASCII characters associated with each of the bytes in that row to display on the right. We also highlight that one if it's selected. These two helper functions are nothing special, some cursor conversion math and the setting of color strings. And now to munge the data from our app state, we'll need to wrap the memory unit in our state so we can access the bytes. There's a weird thing that happens with memory. It's not copy, and so mutable can't handle it. So I've created a wrapper, a mutable effect container. We really don't need the memory struct itself flying around our streams. It's effectively a singleton. It suffices to have a reference to the stateful data, here state, and a trigger which fires whenever the underlying data changes. For now, it's a read-only mutable because we'll only observe changes to memory, not cause them. In the future, we can imagine making a read-write version of this too. There's a nifty helper function on here to clone the data inside, because I'm thinking it will be a pretty common operation. T in our case is an RC memory, by the way, and so clone effectively just increments the reference count on the memory structure. And now the meat of the component. This function merges the focus, cursor, and memory signals, and reads lots of data from our memory module before creating our view model and making the RC virtual node from our other function. And now let's play with it. Notice we have our table. I've pointed the memory viewer at the part of the memory map that's set to the boot ROM, but don't call the cops. I specifically only show the first half of the boot ROM, which omits the potentially copyright infringing Nintendo logo data. But you can follow along with your own copy of the boot ROM if you don't believe me. It starts with 31, FE, FF, etc. This is the boot ROM, and it's being pulled from memory. And notice we have one byte highlighted both in the hex view and the ASCII view. And if we click around, we can see it changes. It works. I didn't show you one bit though. How does this all fit together? We have a top-level app component with our top-level state. We have some globals, as I said earlier, and then we have one field per component. In this case, there's only the mem view state, and then Some other fields of things that may be shared. I figure we might as well have memory in a separate spot because it's going to be used by separate modules. The app component combines a dummy global value and our two components, each initialized with pieces of the application state. Any piece of it that needs to be shared between more than one subcomponent has to be wrapped in an RC in order to make the ownership semantics happy. That's why the mutable effect of memory is wrapped in an RC and needs cloning. And then we use our inject node hack so we can create our final view. Back at the top level, which is currently in lib.rs, we can create the app state. It's basically just sprinkling RC news everywhere. And towards the end here, we run the top level app component with a reference to the app state and tick the signal future once before running the rest of the code as usual so that we can put ourselves in the initial state and so that we can grab a handle to the canvas. Finally, we can tick again in our request animation frame, and that makes the whole thing go. We did it. We handled our little legal issue. We talked about UIs in the abstract, then in Rust. We worked through the type Tetris until we could get something working, learning a little bit of Rust in the process. And then we built some components, one of which is actually pretty meaty. See you next time.